what I'm saying right now. What I'm saying, sharing right now, I'll again explain to you for the sake of recording. Very, very important. Pay careful attention. Many times students don't understand this concept of limits. They That's why they struggle. Okay. So here I'm what I discussed today is that if a function is well defined at a point and it doesn't have a denominator, then limit as x tends to that point, okay, is same as the function value at that point. Simple. So, and we discussed certain properties that if limit f of x as x tends to a equal to L and g of x as x tends to a equal to M, then if you multiply the function with k and apply the limit as x tends to a, limit gets multiplied k times. And if you add or subtract k, the limit will get added or subtracted by k. F of x power k, the limit becomes L power k. And if you have a sum like this of two functions, one is tending to L, other is tending to M, then it will be this, just replace L and M, P times L plus or minus Q times M. If it's a product of the limits, like that. If it's ratio, then it's a ratio of the limits, as long as they're not equal to, at least the denominator is not equal to 0. So here we took examples. Limit x tends to 2 x square minus 5x plus 10 by x minus 1. You can directly substitute because neither numerator or denominator going to 0. You get the value 4. Limit of sin x as x tends to pi by 2 is 1. Limit of cos x as x tends to 0 is 1. Limit of log x to the base 2 as x tends to 4 is log 4 to the base 2, that is log 2 square to the base 2. You will get 2. And limit x tends to 0 e power x is e power 0 equal to 1. Directly you can substitute. Now we are coming to an important case. Mostly these are the limits that are obvious and these are not discussed. All problems are centered around these indeterminate forms. What are those indeterminate? Now limit f of x as x tends to a is equal to L. Let limit f of x as x tends to a be equal to L and limit g of x as x tends to a be equal to M. And the quotient f of x by g of x is L upon M. So if L equal to 0 and M equal to 0, then it becomes 0 by 0 form. And if L equal to infinity and M equal to infinity, then the limit becomes infinity by infinity form. So what does this mean? L equal to 0, M equal to 0. It means that the function is approaching L. That is, function is approaching 0. G of x is also approaching 0. They are not equal to 0 unless the function is a constant. They are approaching. So numerator. So let us consider 0 by 0 form here. What I am explaining is 0 by 0 form. Suppose f of x tends to 0 much faster than g of x. Then the ratio of the limits will be equal to 0. The ratio of the limit of f of x upon g of x as x tends to a will become 0. Now if g of x tends to 0 much faster than the numerator, then this will the ratio will approach infinity. Okay, we'll discuss these cases. Right now I'll give examples and discuss. But then suppose these two approach 0 at the same rate, maybe with a factor difference, then the ratio will be equal to that factor. So let us consider this example. Limit x tends to 0. I have simple x power 5 plus x square upon x. Okay. Now you look at this. What happens? Limit, you can write this as x tending to 0. You can pull out x square, x cube plus 1 divided by x. Now what happens is both are numerator is going to 0, denominator is going to 0. However, numerator is going faster to 0. All right. So you substitute. So because x is not equal to 0, you can cancel off x. When you cancel off x, you will get x into x cube plus 1. You get 0 into 0 plus 1, which is equal to 0. All right. Now the same thing I reverse. Limit x tends to 0, x upon x power 5 plus x square. Just the reverse. I'll get limit x tends to 0, x by x square, x cube plus 1. I'll get limit x tends to 0, 1 upon x into x cube plus 1. I get 1 upon 0 into 0 plus 1. This is going to infinity. This is going to infinity. So numerator is going to 0, denominator is going to 0. Okay, but which is going faster to 0? In the first case, numerator is approaching 0 faster. It is x power 5 versus x, or more appropriately x square versus x. So you get 0. In the second case, denominator approaches 0 faster. Now I do look at this. Limit x tends to 0. 6 x power 6 plus 5x power 4. Okay. I would not say 5x power 4. I'll do say 4x power 4, some common factor. Then I have x power 4 plus x square. Sorry. X power 6 plus x power 4. Yeah. So numerator and denominator both are approaching 0. Now I can write this as 2x power 4. I can take common. It will become 3x square plus 2. 2x power 4, if I take common, you'll get 3x square plus 2 divided by x power 4 into x square plus 1. Now when you observe this, because x is tending to 0, x is not equal to 0, we can strike off x power 4. Now you can apply the limit. You will get 3 times 0, 2 into 3 times 0 plus 2 by 0 plus 1. So you get 2 times 2, which is 4. So limit x tends to 0 is equal to 4. Now numerator is approaching 0, denominator is approaching 0, but the ratio is approaching 4. In the previous two cases, numerator is approaching 0, denominator is approaching 0, but in one case the limit goes to 0, another case limit goes to infinity. So these 0 by 0 forms, or infinity upon infinity forms, or 1 raised to the power infinity forms, these are called as indeterminate forms. We'll come to 1 raised to power infinity later when we do exponential limits, but these are called as indeterminate forms. So for these indeterminate forms, there are standard results. Now we'll look into that. What are those standard results? So standard limits. You got the concept of indeterminate forms. After that, first case is this algebraic limit. Limit x tends to a, x to the power n minus a to the power n by x minus a. This is equal to, now this numerator goes to 0, denominator goes to 0. However, the ratio goes to n, a to the power n minus 1. Okay, this is a standard limit. So proof for this. Now we can write x power n minus a power n as x minus a times x power n minus 1 plus x power n minus 2 times a plus x power n minus 3 times a square plus x square into a power n minus 3 plus x into a power n minus 2 plus a power n minus 1. Okay, so this is what it is. So x power n minus a power n by x minus a. This is a standard expression for this product. This is a standard result. Now this becomes equal to x power n minus 1 plus x to the power n minus 2 times a, x to the power n minus 3 times a square, x square into a power n minus 3 plus x into a power n minus 2 plus a power n minus 1. Now when you apply limit x tends to a, you can replace this as limit x tends to a, this whole expression here on top. Now when you substitute, now this is like a polynomial. For polynomial, you can directly substitute the value to which x is tending to. Ask her to sit. So this will be equal to a power n minus 1 plus a power n minus 2 times a, so on, a into a power n minus 2 plus a power n minus 1. So how many times? This will be n times. If you observe this very carefully, this is n times a power n minus 1. Okay, so this is the standard limit. Okay, limit x tends to a, x to the power n minus a to the power n by x minus a is n a to the power n minus 1. Next, we'll look at trigonometric limits. Are you all able to hear?
Yes, sir.
Trigonometric limits. Now, they are standard ones. First, we will take one very important limit. Limit x tends to 0 sin x upon x. Many times students just mug up this formula and they say whenever they say sin x by x, they put it equal to 1. No, this is as x tends to 0, sin x by x becomes equal to 1 because sin x extending numerator is tending to 0 and denominator is tending to 0. Okay, so how does this happen? I'll show graphically and then I will show you a geometric proof for you to understand. So this is sin x graph, okay, and this is y equal to x graph. So sin x and x. So now you see, I'm trying to approach closer and closer to 0. Now sin x is equal to 1 when x is, pi by 2, 1.57. And at that point, 1.57, this is 1.57, x is 1.57, y equal to x. Now you see the graph. Here, there is a difference between y equal to x and sin x. But as x approaches 0, all right, are you able to see the arrow, the cursor, as I'm indicating? As x approaches 0, the sin x graph and y equal to x graph, they are coinciding, you see. Now I'm going closer and closer to 0. I'm going closer and closer to 0. You are not able to make any distinction. Correct? I am approaching more and more closer to 0. We are not able to see any distinction with the graph. That means x and sin x have merged pretty much. So as x tends to 0, sin x is almost equal to x graphically. As x approaches 0, sin x is equal to x, in fact. So the limit therefore becomes equal to 1. Okay, this is a trigonometric limit. Now, next, I'll explain to you this with a geometrical proof. So now let us take a circle, a unit circle. Just a second. So this is a unit circle. Unit circle means circle with radius equal to 1. Radius is equal to 1. Now this is the center. This is a chord. Sorry, this is the radius. And extend this to this. Now, let us say there is another chord. Sorry, another radial line at an angle of x. Let this point be B. Okay, let this point be B. Now, I will draw a tangent. Just a second. This is not responding. Yeah. Now I'll draw a tangent at B. Now tangent at B cuts this point as say M. Now one more thing I'll do is I'll drop a perpendicular from B onto this line and let us be N. Okay. Now observe this carefully. This radius is 1. Okay. Now if you observe this figure, area of triangle OBN, area of triangle OBN is less than area of the sector of the circle OAB, which is less than area of triangle, which is less than the area of triangle OBM. Got it? Less than the area of triangle OBM. Area of triangle OBN is lesser than the area of the triangle lesser than the sector OAB, this area of this sector, and this is lesser than the area of the triangle OBM. Clear? Clear to everybody? Are you able to see this clearly?
Yes, sir.
Now, you see, area of this triangle will be half base into height. Okay. Now, what is the area of this triangle? We'll see. OBN. This is 1. This is cos x. And this is, this length will be cos x and this length will be sin x. Okay. So area of the, no, I will not take this triangle. I'm sorry. I will take this triangle. I'll not take that triangle. I'll take triangle. I'll erase this. Right. Area of the triangle OAB. Understand? Area of the triangle OAB less than area of the sector OAB less than area of triangle OBM, right? This is now from properties of triangle. This length is 1, this length is 1, this length is x. From properties of triangle, the area of this triangle is half sum of the edges, half into product of the adjacent sides into sine of the half base into height. Say height for this is this perpendicular, and sine x is opposite side, sine of x is opposite side, this bn upon OB, which is 1. Sine x is bn upon OB, which is bn upon 1. So sine x is nothing but your height of this triangle. Okay, the height of this triangle is sine x. So half base into height. Half base is 1, height is sine x into 1. So half base into height. All right. Next, area of the sector OAB is half r square theta, 1 square times x. Area of the sector of a circle, half r square theta. And area of this triangle OBM. OBM. So this height BM. Now you see this triangle, this is a right angle triangle. BM, because this is a radial line and this is the tangent. So this is a right angle triangle. This is your base. We want for a right angle triangle half base into height. This height BM is tan x. Tan x will be equal to BM upon 1. So this is equal to tan x, half into 1 into tan x. Okay, so here we get a very, very important inequality. From your board's point of view, this is not at all, they don't even discuss this. But from competitive exams point of view, this inequality will be a very, very important inequality for you. Sin x is less than x, tan x for all x belongs to 0 to pi by 2. Very, very important, extremely important. Now what happens? Now, as x tends to 0, now as x tends to 0, that means B moves towards A. Point B moves towards A on this circle. You see here. Then what happens? As B comes closer to A, this point N and this point M merge onto A, isn't it? They will merge onto A. So then what happens? All the three areas practically merge to a single area, and all of them are tending to 0. Correct? When B up over on the circle, this point B is approaching the point A, then your triangles will become smaller. Like this, I'll draw again. This is A. Now this is, let's say, point B. B is approaching A. Then what happens? There is hardly any difference between the sector and even the tangent. And when B moves closer and closer to A, this difference will still exist, but very, very, very small. So sin x is almost equal to x is almost equal to tan x. All right. Therefore, this limit x tends to 0, sin x upon x becomes equal to 1, because this is tending to x. So first I showed a graphical proof, then I explained a geometrical proof. Okay. So standard limits. So again, I remit now. Limit x tends to 0, sin x upon x is equal to 1. Limit x tends to 0, tan x upon x is equal to 1. Now there are variations of this. Limit x tends to 0, sin x upon tan x, this is equal to 1. Tan x upon sin x is equal to 1. Then limit x tends to 0. Now sin 2x upon x, or sin ax upon x, sin ax upon x is equal to a. Limit x tends to 0, tan ax upon x, this will be equal to a. Why? Because you multiply and divide by, I'll explain that. This standard list of you, right? Limit x tends to 0, sin ax by tan bx, this will be a by b. These are all standard trigonometric limits of 0 by 0 form. All are 0 by 0 form. We are talking about indeterminate forms. Within indeterminate forms, we are talking about limits of 0 by 0 of trigonometric nature. So now let us look at this D part. Limit x tends to 0, sine ax upon x. We can write this as limit x tends to 0, sine ax divided by ax multiplied by a. Okay. Now ax you can replace by y. Let y equal to ax. Now as x tends to 0, y will also tend to 0 because constant multiplied by a number approaching 0 will also approach 0. Okay. So now you can replace this one. So now you can replace. So the limit becomes limit sine of y upon y into a as y tends to 0. Understand? This one I have put like this. So this is sine y upon y is this one. Sine x upon x is equal to 1. Sine x by x is equal to 1. So limit sine y by y. So this tends to 1 times a. This is equal to a. So directly we have written this as a here. Limit sine ax by x is equal to x is equal to a. Okay, okay, Kira.
Thank you, sir.
So tomorrow's class, I'll end here. Tomorrow's class, we will continue. I have just given two limits. One is algebraic limits, and other is trigonometric limits. This entire set. We will do problems on this. And I have to do existence of limits using left hand limit and right hand limit. These two things I have to do. Okay. So for tomorrow's class, I'm writing so that I will have. So we will do problems on algebraic limits, trigonometric limits, and we will do existence of limits using left hand limit and right hand limit. So these two problems we'll do. It's a very important class. Please attend. Okay, we'll stop for now.